Every night across the skies around the world there is a battle raging between predator and prey that we cannot really see or hear. Many species of bats are ferocious predators of nocturnal insects, hunting them in the darkness using echolocation to illuminate the world around them. They send ultrasonic clicks through their mouth or nose and listen for echoes bouncing off objects with highly specialised hearing apparatus. One of their favourite nighttime snacks are moths. Moths, however, are not completely defenceless, with different species evolving various strategies to try and help them avoid becoming lunch. Some moths will fly erratically to try and avoid being captured, others have evolved ears so that they can hear a bat approaching and fly away, while some even produce ultrasonic clicks of their own, warning a bat that they are toxic and not to be eaten. We are interested in passive defences. These are defences which are always there regardless of whether the moth knows a bat is nearby or not. We have previously shown that the fur and scales of moth wings are excellent sound absorbers, providing some moths with acoustic camouflage against bats. Another strategy, however, is to make part of your anatomy give off very strong echoes, with the hope that this would divert the bat's attack towards them and away from the precious and vulnerable body of the moth. Some silk moths have been shown to possess acoustic decoys, like this American lunar moth I have here. Now this moth has evolved elongated hind wings which terminate in this twisted and cupped structure here. It's been shown that these hindwings are very strong reflectors of sound, so much so that a bat attacking this moth is more likely to head towards the decoy rather than the moth itself. We notice that on many of the larger silk moths, the four wingtips are actually folded and rippled in a way not too dissimilar to the hindwing decoys that we looked at earlier. This got us thinking, could these wingtip morphologies offer a similar protective benefit to the hindwing decoy? So we devised a set of experiments to test this. We use acoustic tomography to get echo measurements of moths with different forewing morphologies from thousands of different sound incident directions. Here we are hitting a moth specimen with ultrasound and using a microphone to record the echoes. This allows us to measure which parts of the moth give off strong echoes and which parts give off weaker echoes. If we found that the wingtips were giving off consistently stronger echoes, this would imply that the wingtips were indeed acoustic decoys.
So what we found can best be summarized on this composite image. So on the right you can see the atlas moth, on the left you can see the same one, but imaged by sound, and the false colors we have here tell you which body part reflects how much sound energy. You can see that this is measured in target strength, which is just an indicator of the amount of the incident energy being reflected back. And red means that more sound is coming back than at the other colors. And what you can see is that very clearly in this leading edge curved area, there is a strong red line indicating that most energy is coming from there. The rest of the wing is far less reflective. And this region coincides with the rippled area on the forewing, as you can see on the right hand side. So clearly most acoustic energy comes from the rippled area. So on this slide, let's try and be more specific about what much louder means. This plot shows you the difference in echo strength between the body and the decoy. That could be the decoy at the wingtip or a decoy at a hindwing. And we measure this as target strength difference. Let's start with the no decoy case, the gray curve. That's a species that doesn't have any decoy, and we are comparing the forewing area to the body, and we can see the body is always much louder, around 10, just over 10 dB louder than the wing, and that would be indicative of most of the attacks going to the body. Going one curve up to the green curve, the hindwing decoy, that's the lunar moth Tom has just shown you, and that one has about the same amplitude in its echo as the body. So in that case, acoustically speaking, the bat should have about a 50-50 chance of attacking the body or the hindwing decoy. Now the most interesting part is the red curve on top, and that's our forewing decoy of the atlas moth. And you can see that for most frequencies, the decoy produces a louder echo than the body. Only at the very lowest frequencies isn't that the case. And the reason for that might mean that it's not designed to increase the detectability, but only kicks in when the bats start using higher frequencies during attack. But that remains to be confirmed. So now we know how much acoustic energy is coming off these regions. Let's think about how this energy is sent back to the echolocating bat. And we have identified two different types of so-called retroreflectors. Retroreflectors are structures that somehow send sound back into the direction it came from, irrespective of where it came from. And the two designs that we found are either hemispheric retroreflectors or dihedral corner retroreflectors. In both cases, the sound is reflected not once, but multiple times, 2 or 3 times, to create an overall reflection angle of 180 degrees. Let's just assume the 2 reflection case. In a hemispheric retroreflector, the sound hits one wall, is bounced off at 90 degrees, hits the opposite wall again, reflected at 90 degrees, and that would add to 180 degrees and reflect back towards where the sound came from. For that, you need hemispheric structures like the ripples in the wing, and they need to have an opening angle of more than 90 degrees. In this case, we have 115, so that should be functioning over a relatively wide range of angles. So the ripples are hemispheric retroreflectors. What are corner retroreflectors? They are a bit simpler. They also work with double reflections, but here they're reflected from 2 flat surfaces, planar surfaces that meet at about 90 degree angle. And then again, you've got one reflection at 90 degree, another reflection, and they add up to 180 degree, which results in retroreflection. Both together give these wingtips their remarkable, loud, and more importantly, omnidirectional echo decoy functionality.